Hello, this is Lec4-stat134. You guys get to look forward to having a quiz on next Wednesday, just to know, and it's going to be on Chapter 1. So what did we do last time? Last time we finished what we're going to cover in Section 1.6, which is the multiplication rule for three independent events. And you can visualize this as a tree. So the top branch of the tree is the chain A, B, and C, all being true. So the probability that you have A, B, and C then would be the product of these unconditional probabilities. That's what the multiplication rule says for independent events. And you can see that, for example, it would require that the probability that C conditioned on A and B being true should be the same as just the probability of C. And that's not something that's going to follow from pairwise independence. So independence is a stronger condition than pairwise independence. And I illustrated this with the birthday example from the end of last class. Now what we're going to focus on today is the binomial distribution. So the binomial distribution is probably the most important distribution. It comes up in lots of applications. We start off with a Bernoulli p-trial. A Bernoulli p-trial is the simplest kind of binomial distribution where we just have two outcomes. The outcome of a success has probability p, and the outcome of a failure has probability 1 minus p. So for example, you roll a die, say that you get getting a 6 is what we call success. Not getting a 6 is a failure, and probability of a success then is 1/6, probability of a failure is 5/6. So the binomial distribution, we suppose we have n independent Bernoulli p-trials. So the key here is independence. So for example, we roll a die n times. So what are the possible number of successes? Well, we can have anywhere between 0 and n sixes if we're rolling a die n times. So what's the chance of getting, for example, 2 6s in 5 rolls? So there are many ways that we can get 2 6s in 5 rolls. Let's enumerate them. So for example, we could have 1 1 0 0 0. That means we get 2 6s in a row followed by 3 non-6s. This is probability 1 6 squared times 5 6 cubed because of we're assuming independence, and that follows from the multiplication rule applied to 5 events. And but there are other orderings. You could have 0 1 1 0 0, which would have the same probability. And so you can quickly see that all the ways that you can get exactly 2 6s in 5 rolls are going to have the same probability, and we just need to count how many there are. So the answer is 5 choose 2, but let's do an aside on counting to show why that's the case. So how many orderings are there of 5 distinct elements, A, B, C, D, and E? So the answer is 5. That's right. So you have 5 choices for the first, 4 choices for the second slot, 3 choices for the third slot, 2 choices for the fourth slot, and 1 choice for the last slot. So that gives 5 times 4 times 3 times 2 times 1, which is 5 factorial. So how many orderings, for example, of AA, BBB, if in this case A and A are indistinguishable and the 3 B's are indistinguishable? Well, it's going to be less than 5 factorial, right? So we can we have duplicates of AA, BBB. How many duplicates do we have? We have 2 factorial, 3 factorial, which is 12 duplicates. And similarly, we would have 12 duplicates for other orderings. For example, AB, ABB would also have 12 duplicates. So what we need to do is we need to divide the 5 factorial by 2 factorial, 3 factorial. And that we define as 5 choose 2. So basically, out of the 5, you're choosing 2 to be A. That ends our aside, and then we can quickly see why here the number of ways we can get 2 6s in 5 rows is 5 choose 2. So we get the probability of having 2 successes is 5 choose 2 times p squared times 1 minus p cubed, where p is 1/6. More generally, find the chance that you get exactly k successes out of n Bernoulli p trials. That would be the probability that you have k successes is n choose k, p to the k, 1 minus p to the n minus k. And this is known as the binomial formula. So the ingredients for the binomial formula is you need n independent Bernoulli p trials, and you need k successes. So then we did an example where we tossed a fair coin 5 times, and we asked, what's the probability that you get at least 3 heads? Well, there are different ways you could get at least 3 heads. You could have HHHTT and various orderings of that. So the probability of getting exactly 3 heads we know is given by the binomial formula. But you could have exactly 4 heads, or you could have exactly 5 heads. And these are all mutually exclusive, so we just need to add up those probabilities. We then did a concept test where I asked you guys to check off which of the following 2 scenarios the binomial formula applies to. And the answer is just the first one. So in the first one, we see that we are drawing with replacement, so we're going to have independence. Now, the sum of draws from a 0-1 box is the same as saying the number of successes, since, for example, if I have 3, if the sum of 5 draws is 3, that means that I have 3 1s and 2 0s, right? So I know how many successes I have. So we have independence, we have n is 5, and we have p is 1/10. Now B, however, we do not have independence because we're just drawing off the top of the deck and not replacing the card back into the deck and reshuffling. So we know that the chance of a diamond is always, there are 4 diamonds in the deck, so it's always 4 out of 52. I'm not making a conditional probability. I'm saying the probability of an ace on the top, for the top card, is always 4 out of 52. But I'm drawing off and not replacing, so I do not have independent draws. We then looked at the consecutive odds ratio, which for us is just a tool to find the mode of the binomial distribution. And the mode is the most likely outcome. In other words, the k such that p of k is largest. So here we're going to use some facts here that are proved at the end of the notes. And what I want to make sure is that you understand how these facts apply. So what the first fact says is that the probabilities increase exactly when k is less than np plus p. So again, n is the number of draws, p is the probability of a success, and k is the number of successes from your binomial formula. So this is applying to a binomial distribution. For the second statement says that the distribution decreases exactly when k is greater than np plus p. And the third statement says that probability of k minus 1 and probability of k are the same when k is np plus p. So let's decipher this with an example. So assume that np plus p is 7/2. Okay, so I've drawn this here. So 7/2 is a half integer. So the third case is not going to apply. Now, when k is an integer, right? K is a whole number. So when k is less than 7/2, then we're increasing. So that's what I've shown here by 1. And then when k is greater than 7/2, it's decreasing. So that's what I've shown here by 2. Now, if np plus p is 4, for example, then we're increasing up to 3. Then, and that's by 1. Then by 3, we see that p of 3 and p of 4 are the same. So that's what this is by 3. And then after 4, so 4 and after 4, we're decreasing, and that's by 2. So there you go. Yeah. Okay, so let m be the floor of np plus p. So that just means the integer part of np plus p. For example, the floor of 7.2 is 7. So we define the mode as follows, right? So the mode, we're going to break it into two cases. So if np plus p is not an integer, so let's take a look in this case. So here, if it's a half integer, so we see we have a single mode. So the single mode here is 3, right? So it should be the integer part of np plus p. So we say the mode is m, the integer part of np plus p. And if np plus p is an integer, so in that case we have this picture here. So so we have two modes, right? 3 and 4. So in that case, m is 4 in this case. So 4 and 3 are both modes. So m minus 1 are modes. Now, as for the proof of the fact above,